All right, for lesson 2 of chapters 8 and 10, looking at the difference between relations and functions. Section 1 was all about relations. So anytime you have an x and a y relationship, that just means two things are being compared to each other, so that's a relation. Two things are being related to each other. But a function is a specific type of a relationship. So in order for something to be a function, it's got to fit certain criteria, and so that's what we're going through mostly within today's lesson. So let's start going through a few examples on this. So if we're going to test to see whether or not something is a function, then we got a couple ways of doing that. We can do it algebraically, we can do it graphically. So we're going to show you a couple different ways that you can determine whether or not something is a function. So starting with our first example, if we were to test this just algebraically, testing it algebraically would mean that I simply need to get y by itself. And then I'll kind of show you from there what we would do. But if I were to get y by itself, we would start by adding the x over to the other side. Then I would cube root both sides in order to get y by itself. So I'm looking at the cube root of x plus 2. And the way to test this algebraically is simply this. If I plug a number in for x, will I always get only one solution to go with it? So could I ever plug in a number for x? Let's just pick a random number. Let's just pick 4. Now let's pick 6. If I plugged in 6 for x, am I only going to get one result from that, or am I going to get two separate results? If I plugged in a 6, well, 6 plus 2 is 8. The cube root of 8 is 2. I get exactly one solution for that, so I know that this is a function. When you're determining whether or not something's a function, think of it in real life terms. If you were talking about a machine, let's just say you have a machine that produces Pepsi, and so if you put certain ingredients into that machine, it should only produce one item. It should only produce one result every single time. If I put the ingredients into my machine for Pepsi, I expect to get Pepsi as my result. If I could put the same ingredients into my machine and get different results, one day I got Pepsi, the next day I got 7-Up, the next day I got Coke, we would say the machine is not functioning properly. So in order for the machine to function, you can only get one result when you put something into the machine. And so that's the idea here. I'm putting one item into the machine, and I'm only getting one result to go with it. And so that's why this equation is a function, or it is functioning properly. You'll see an example down here of when you can get two different results for the same input and why it's not functioning properly. But before I get to that, as I mentioned, there's two ways to determine whether these are functions or not. One is algebraically, as I just showed you. It's one input for one output, so we know algebraically that is functioning properly. We could also look at this graphically, though, as well. So if we were to throw that into our graph and graph the function, the cube root of x plus 2, so let me throw that in really quick. So the cube root of x plus 2, and graph that. You learned something a while ago as far as testing these, which would have been as early as Algebra 1. We do something called the vertical line test. And the vertical line test just says if I can draw a vertical line anywhere on this graph and only hit the function one time, then it passes the vertical line test, therefore it is a function. And you could see this one would pass the vertical line test. There's nowhere on the graph that I could draw a line and hit the graph twice. I'm only ever going to hit the graph once, so we would say it passes the vertical line test, and yes, it's a function. So those are always two ways that you can determine whether or not something's a function, algebraically or graphically. So looking at our next example, let's do the same thing. If I get y by itself, so I'm going to subtract my x over to the other side, so negative x plus 2. I'm going to square root both sides to get y by itself. Well, what's something you've always had to do anytime you square root both sides of an equation? Right? You've always had to throw in a plus or minus to go with it. And so I get this look here. Well, let's test a number here. Can I plug in a number for x and only get one result? So let's just test a number. I'm going to pick -2 to sub in. So negative 2 would be positive 2, plus 2 is 4, and the square root of 4 is 2. But notice I'm getting two solutions. I'm going to get positive 2 and negative 2 as two solutions. So I'm only putting one item into this equation, but I'm getting two different results in the end. And so we would say this machine is not functioning properly. So this is not a function because I'm getting two different results for the same input. And so we'd say that it's not a function. And that's, again, the algebraic way of testing that. Let me show you how you could, again, do this on your calculator. So I got to put in, keep in mind here, I have to put in the positive square root of negative x plus 2 as well as the negative on that. And so I'll just start with the positive, but we'll say the square root of negative x plus 2. I also have to put in the negative square root of negative x plus 2. And so I have the entire function. I had to do the plus and the minus. And so now when I graph this, so you're going to see here, because of the plus and the minus, you can see the plus is in blue and the minus is in red. Because I have both, it would fail the vertical line test, and therefore it's not a function. Right? 'Cause obviously I can draw a vertical line and hit the graph twice, so it's going to fail the vertical line test. So we can look at it either way. In either case, it's not a function. Example 3, we can do it with ordered pairs as well. The easy way to look at ordered pairs is simply, do you have any x's that repeat? If they're all different, then we're good. This machine is functioning properly, and so that would, yes, be a function. If you want to look at it graphically, well, graph those 3 points. Does it pass the vertical line test? Right? We can see that it does. It does pass the vertical line test, right? I'm never going to hit 2 points with one line here. So it passes the vertical line test, so yes, it's a function. One thing, just a reminder on example 3 here, is oftentimes people forget, should I be looking at the x's or the y's? Notice I do have repeating y values, but that's okay. As long as the x's don't repeat, then we're good as far as this still being a function. If your x's repeat, that means you're going to get a stack of points on top of each other, and it would then fail the vertical line test. So that's what you're looking for on that. So looking here at example 4, very similar idea of what we've already been talking about, but there's some extra notation thrown in here that does affect the results that we come up with as far as whether or not something is a function. So if you look at the first example, so y squared equals x, well, when I go ahead and square root both sides, remember I have to throw in a plus or minus when I square root both sides. And as we already saw up above, because of the plus or minus, it's going to fail our tests for being a function. And so we already know this is not going to be a function. I wanted you to see the one extra notation that they threw in here. How does that affect this guy as far as whether or not it's a function? All this is telling me is that I can only plug in x's that are 0 or greater. Well, we already know that's true because in a square root, I can't square root a negative anyway, so this is only there to simply tell me, hey, when you start plugging in numbers for x, make sure that you're not trying to square root negative numbers. You can only square root 0 numbers or positives, so those are the x's that you're allowed to sub in. So let's just test one. If I test an x value that's greater than or equal to 0, like 9, what kind of results do I get? So if I plugged in a 9 for x, square root of 9 is 3. And according to this, I get positive 3 and negative 3. So I'm getting two different results, which means this guy is not functioning properly. It's not a function because I'm getting two different results for only one input. I'm putting in 9 and I'm coming away with positive 3. Then I put in 9 and come away with negative 3, so I'm getting two different results for the same input, so it's not a function. And as we already saw earlier, it would fail the vertical line test, and you can always test that on your own on your calculator. Here's the difference with part B. In this one, I'm still looking at the same function, and I'm still going to square root both sides. All right, so I'm still doing this, and I'm coming out with y equals positive or negative x, but here's the difference. The notation on this side is now saying I can only get y values that are greater than or equal to 0. So what is that telling me? When I plug in the same number, let's just plug in a number like 9. The square root of 9 is positive 3 and negative 3, but according to this notation, I'm only allowed to keep the results that are greater than or equal to 0, which means I'm not keeping the negative result. I'm only keeping the positive result. So if I eliminate the negative result, so by eliminating the negative result and only keeping the positive result, I now have a function because I'm only now getting one result for my input. And so if we were to graph this one now, let me just throw it on here really quick for one more graphing example. But now if we were to graph this, it's this same idea where if I eliminate the negative version of my answer and only keep the positive version, right? So now I'm only keeping the positive, now it passes the vertical line test, and now it's a function. And so you do have to take into account some special notation that they might throw in that does allow it to be a function, like this one does. So moving on down here, so in part 2, these are now just a matter of kind of subbing in numbers and getting some results. So we're given a function like this. It says that your x's are all elements of the real number system. So let's find a few things. When they say something like f of 6, that means I am subbing in a 6 for x here and here. And we're just going to clean that up as much as possible. So replacing my x's with 6's, I get this look here. And if we just do a little cleanup, 6 squared is 36, minus 3 is 33. So that's the result that we come out with. Notice the left side of this equation, that's just notation. Oftentimes, I still get students who want to like solve for f, and they try to like divide 6 over to the other side. Right? That doesn't make any sense. This is just pure notation. All this tells anybody is that I plugged in a 6 for x. You don't do anything to this side of the function. It's just a notation. On this side, you can see we're now subbing in x plus 1 for x. So right now we're going to replace our x's with x plus 1. And again, the left side is just notation. The right side is where you do the work. And so I replaced my x's with x plus 1. And if we do a little cleanup, right here you'd have to FOIL. So this means x plus 1 times x plus 1, which is, if you FOIL that out, x squared plus 2x plus 1. I'm going to bring down my minus 3. And now I have one more step because I can combine like terms. So the last step on that would be to combine the constants that we have. And this is where we would finish. So you always simplify as much as possible. We don't want to leave it in this stage. We want to do as much cleanup as we can. So I want you to notice the big difference right here for part C compared to part A. Notice that in part C we're now saying f of x equals 6. This one said f of 6. So when it says f of 6, you're plugging in a 6 for x. But when it says f of x equals 6, right, I am now replacing the entire left side with the number 6. So I am now saying x squared minus 3 is equal to 6, and I now have an equation to solve. I am solving for x. So there's a big difference between A and C that you have to recognize. So in this one, I am now setting the entire thing equal to 6, and I'm looking for a solution for x. So as I continue to solve, I would add the 3 over to the other side. And if I square root both sides, we're going to come away with positive and negative 3 as our two solutions. Don't forget your plus or minus. That does matter. Those are two solutions for that. What about the range of this function? Here's something we dealt with in our first lesson when we did domain and range of functions. So an easy way to look at this, because we know we're going to deal with inequalities here. We know the domain was already established for us The x's are all real numbers, so that was our domain. As far as the range, if you looked at the graph on this, we know that this is a parabola that has been shifted down 3 units. And so if I shift that down to -3, here's the function, and you could always plug this into your calculator and look at it that way too. But this is the graph. So what is the range? Remember, the range is what your graph is doing from bottom to top. And in this one here, it goes as low as -3 and then goes up forever. So we could either write that as y values that are greater than or equal to -3. That is set notation. Or we can use interval notation and say that we are going from -3 and we are heading towards infinity. And so we can use either notation to identify the range. I threw in one last side note down here at the bottom. This is the way we are used to seeing functions in these kind of terms, where y equals or f of x equals. But there are 2 other notations in IB language that you're going to run into, and they look like this. So I just want you to understand that these notations mean the exact same as these notations. So whether you say y equals, f of x equals, this or this, all 4 of those mean the same thing. And so I don't want you to be thrown by that. It's just a different way of writing the notation for those.